Hello and welcome back. So, last class we were looking at the reasons how we can increase the reaction sites. So, how to increase the reaction sites. So, first, as we discussed, we can increase the area of the electrode. So, from let us say 5 centimeter square to let us say 50 centimeter square, then the current that is generated from smaller cell will be inferior compared to that of the larger cell, because the number of reaction sites will be increased. However, there is one, we also need to look at the from perspective from the exchange current. So, we know that this current that is generated in the fuel cell, it is dependent on the exchange current. Higher is the exchange current, higher will be the net current generated in the circuit. I can write this current density is also directly proportional to exchange current density. So, or if I simplify this, I can write this as this I will increase as the area increases, right. So, first one, as we have understood, first one is your geometrical area. Which we actually measure. So, when I say it is 5 centimeter square, we actually measure the length and width of the electrode, and we say it is the geometrical area A. So, let us call this as A. So, let me again do this. This is length into width. So, area is basically length into width in centimeter square or so. There is another area that now we will introduce, which is intrinsic area. Let us call this as A dash. Now, intrinsic area is far different from the geometrical area. It is the actual area of the reaction sites. So, if I zoom in this only small portion of this geometric area here, and if we look at this, it will be, there will be crust and troughs all the way across this electrode, and this area which takes into account the all crust and troughs, or all the small areas that have this that is there in this electrode, is basically the intrinsic area A dash, and this A dash is far larger than the A, because it also involves all the areas through crust and troughs. So, in other words, this intrinsic exchange current density this is J naught dash is far greater than the apparent exchange current density. So, geometrical area is also called as apparent area. Let me write that down. This geometrical area or the apparent area. So, apparent exchange current density J naught. So, let me write this one more time. J naught dash is greater than the J naught. And how are these two related? They are again related by the respective areas. So, if I want to write J naught by J naught dash, or apparent to the intrinsic exchange current density, is related by the ratios of apparent areas and the intrinsic areas. So, if the electrode area is very rough, it will offer more surface area for the reaction. So in other words, we have to have our electrode as rough as possible so that the intrinsic exchange current density becomes larger, and as we know, the exchange current density, once it becomes larger, the current that flows through that electrode in an external circuit will also increase accordingly. So this is all about the theory. Let's quickly go ahead and solve some numericals. So let's take the example. So we have been given current density in milliamps per centimeter square, which is roughly around 40, 43, 47, 50, 54, 58, 61, 64, 69, and the corresponding work potential in millivolt is given as 72.1, 75.1, 76.2, 78.8, 81.8, 83.2, 84.1, 86.7 and 88.8. So this is the data. This data is for the hydrogen electrode. What we have been asked is find out the operating potential when we are drawing current at the rate of 125 milliamps per centimeter square, right, which is not there in this data. So we need to plot this. So if you plot it on an Excel sheet, eta versus ln I, ln Z here. So it will be, there will be a straight line. So there will be points somewhere like this. Few of these points will be on the line, few may be out of the line. However, if we have a common line going through these points, it will be a straight line. As we can see, the over potential is more than 50 millivolt. It is the case of the eta when it is large. So we have to draw this from the line equation. So line equation we get is somewhere around like this, 30 ln Z minus 38.6. So this is the line equation. So let's compare this, comparing with the Tafel equation. What does our Tafel equation say? That eta activation is basically RT by 1 minus alpha NF ln Z minus RT by 1 minus alpha NF ln Z naught, right. This is in the form of, let us say, eta equals m times ln Z plus C. So there is a slope here and there is a constant as well. So we need to compare this. So if we do that, we get T by 1 minus alpha NF as T by ln Z naught as 38.6 minus, so they both become plus, and what we get as an RT by 1 minus alpha NF as 30, right. That is your slope. So let us go ahead and find out the exchange current density. So in other words, this ln Z naught is equal to 38.6 divided by this RT by 1 minus alpha NF, which we have found out from the equation as 0.6 divided by 30. So that becomes exchange current density is somewhere around 3.6 milliamps per centimeter square. Why is the unit milliamps per centimeter square? As we can see, the value unit of the current density that has been given is in milliamps per centimeter square, and that is why the exchange current density will also come with the unit of milliamps per centimeter square. So, let us go ahead and find out for eta, which is given 1 minus alpha nf ln of j by j naught. So, we can either write I by I naught or j by j naught because the area gets cancelled. So, this has been given as 30 from the equation of the line. This is ln j, let me write this as j is what we have to find out, and this is 3.6. Now, operating current density is given as 125 millivolt per centimeter milliamps per centimeter square. So, operating current density is 125 milliamps per centimeter square, which is given. So, let us put that up. So, that is 30 ln 125 by 3.6. Once we do this, we get eta. This is again activation, this is somewhere around 106 millivolt. So, once we find this up, we know eta is E naught minus E. However, in real practice, when it comes to fuel cells, this E naught is typically the open circuit potential. Let me write that, open circuit potential minus the operating potential. This is in practice, we do this. So, let us say open circuit potential in this case is 1 volt. So, 1 volt minus E, and eta activation we have just found out somewhere around 106 millivolt. So, let us convert that. So, this is 0.106 volt is equal to 1 volt minus E. Now, this E is E operating. Let me write this like this, E operating. So, in other words, your E operating, when we are drawing 125 milliamps per centimeter square of current density, it will be 1 volt minus 0.106 close to 0.894 volt. So, this will be the operating potential of this particular cell if we are drawing 125 milliamps per centimeter square of current density, and we will have the total drop of at the hydrogen electrode will be around 106 millivolt. Let us go ahead solve one more simple equation, simple numerical. Now, in this case, line equation is straight away given, 57.241 x minus 127.18. So, let us find out the exchange current. So, once we compare this with the Tafel plot, we can write this as 57.241 ln I naught equals 127.18. So, in other words, ln I naught is 127.18 divided by 57.241. So, that gives us exchange current as 224 milliamps. Let us go ahead and find out the charge transfer resistance as well. So, RCT we will know it is RT by I naught NF. So, this RT by F is a standard number. So, RT by F is 25.6 millivolt at STP. We can straight away use this here. So, it is 25.6 millivolt. This is N is 2 and exchange current is 9.224. this is again in milliamps. So, the resistance value that we get is somewhere around 1.38 ohms. So, how are we getting ohms? Because as we can see, this V equals IR. So, V is in millivolt, I is in milliamps. So, R will be in ohms, right. So, RCT is somewhere around 1.38 ohms. Let us begin with the new chapter about charge transport. So, when we talk about the charges that are flowing in whether it is a fuel cell or an electrolyzer. So, as we know, in case of typically a fuel cell, we have electrons flowing through the external circuit. We also have protons flowing through the electrolyte. So, these are the charges that we will be concerned about. So, first one is the protons, it is H plus, and electrons that flow in the external circuit. So, first of all, let us understand what is the difference between flux and flow rate, because this we will be using this flux in upcoming discussions. So, basically flux is nothing but it is a flow rate per unit area, right. So, in other words, let us say I have a conductor, or so let us say a pipe which is flowing water, and let us say it is 5 liters per second. Water is flowing through this pipe, and this has got area A. This is the cross sectional area A. So, the flow rate will be 5 liters per second, whereas flux is 5 liters per second per unit area. So, this area is let us say in centimeter square per second. So, unit of flux is the volume, in this case volume divided by area per unit time. So, if I simplify, flow rate, that is normalized per unit area is nothing but flux, okay. And flux is normally measured in molar quantities. So, it is called as molar flux. Instead of calculating this on volume basis, we measure it on molar basis. So, it is mole per centimeter square per second. So, this is basically molar flux, okay. It is called as molar flux. So, this is in case of let us say water that is flowing through the pipe, the example we just took. What happens in case of charge? In case of charge, we can write, instead of molar flux, we can write it as a charge flux. So, let me write, in case of charges, it is charge flux. Basically, it is charge per unit area per unit time. Just extending the molar flux definition to the charge flux. So, we have charge per unit area per unit time. So, if I try to find out the unit, charges are in coulombs, area is let us say in centimeter square, time is in second. So, coulombs per second is basically amperes. So, it is basically ampere per centimeter square. And if you look at carefully at this unit, this basically is nothing but our current density. So, in other words, current density is nothing but the flux. So, in case of fuel cells, how are these movement of charges, how do they take place? So, in case of fuel cells, movement of charges, or say electrons or protons, it take place through 3 different routes. So, we are talking about the electrons as well as the protons. So, first is your electrical driving force. So, that is basically dV by dx. So, that is our driving force, potential gradient. So, we also have, this is basically potential gradient. Second one is your chemical driving force, or it is also called as chemical potential gradient. This is basically, we have seen, this is d mu by dx. And third, as you can see, mechanical driving force, or this is also called as pressure gradient, or gradient, which is dP by dx. So, in case of fuel cells, as we understand, let us take this example, H2 giving 2H plus 2 electrons. So, how are these electrons basically? If you look at this, these electrons accumulate and get consumed at both respective electrodes. So, at anode and cathode, and this creates voltage gradient. This is with respect to electrons. Second, in case of protons, and protons also accumulate and deplete. So, what happens basically in case of, let me explain this, in case of electrons, once they get generated here at the surface of, catalyst at the anode side, this is our anode and this is cathode. So, they get accumulated and they get consumed on the cathode. So, this basically creates the voltage gradient, and that is why the electrons flow. What happens in case of protons? Once they get generated here at the anode, this swiftly get into the electrolyte, and once they accumulate here, this, as and when we start fetching the current, the protons also travel and get depleted at the cathode side. So, this accumulation and depletion of protons also happens in the electrolyte. And which basically causes voltage and concentration gradient. However, in both of these gradients, which one dominates? However, this voltage gradient dominates all the time. So, the voltage gradient that gets generated because of the flow of electrons, that also becomes responsible for protons to flow from anode to the cathode, and that is why this voltage gradient dominates the electrolyte. And how do we write this up in case of current density? So I can write this like this. Thus, this current density is function of one parameter called as sigma times dV by dx. Now, what is this sigma and dV by dx? As we know, this dV by dx is your electrical driving force. And what is the sigma? Sigma is nothing but the conductivity. So, it is not only the material that flow through which the different spaces flow, different charges flow, it is also their conductivity that matters when the specific charges they flow through that particular material. So, we have to take into account its conductivity. So, let us draw this general conductor, let us say, then we are passing J amount of charges per unit area, and the length is, let us say, L of that conductor is L. This is a very uniform conductor, let us assume a uniform conductor, and the resistance as it is L by sigma A. Sigma is the conductivity, which is 1 over the resistivity. L is the length and A is the cross sectional area of that conductor. So, if I want to transfer this charges, there has to be potential difference or the energy that we need to lose. So, this is 0 to V, this is 0, and this, so this is the potential difference V over L, which is lost while we carry this current I through this conductor having resistance R. So, this is the energy that gets lost in taking this I amount of charges per unit time from surface A to the other end through this conductor having conductivity sigma. So, let us write this up. So, this is, let me write, this is a uniform conductor. Okay. So, I can write V equals IR, which is our conventional equation. So, I can rearrange this. I can write I equals R is substituted by L by sigma A. So, this resistance, R is your resistance, which is L by sigma A, and this V is nothing but the voltage lost or in other words, I have to better write applied, excess voltage applied to transport the charge at rate I, right. So, this is what, so we need to apply that excess voltage in order to bring that charges at the rate I from one surface to the other or one end to the other. So, this is a loss and this is a loss. Now, why is it loss? Because it is an excess potential that we need to apply apart from what we are doing. So, this is the loss to the system. So, it is a loss incurred due to conductor's inherent resistance to charge transport, right, and that is why this V equals IR can be better written as, this V is potential, basically excess potential, so it becomes eta, and this becomes eta ohmic times I times R ohmic. So, that becomes the ohmic resistance, and eta is the over potential that is we have to apply, or we have to excess energy that we need to supply in order to bring that I amount of charge per unit time from one end to the other. And this ohmic resistance is sum of two resistances, primarily electrical resistance and the ionic resistance. Let me write this. This is R electrical is the resistance of individual cell components or the cell components or the stack components And what is this ionic? Is the resistance of the electrolyte. And as we can see, this, let me write it here, this ionic is far larger than the R electrical. In other words, electrolyte's resistance dominates when it comes to the ohmic overpotential. So, we will take on this ohmic overpotential and the details in the upcoming class. Thank you, sir, very much.